Hello, welcome to A-Level Physics Sister Lesson. My name is Mrs. Daniels. I'll be one of your physics teachers. Before we start today, I just want to make sure you have the things you'll need to carry out the activities in this session today. You will need a notebook to write in. You will need a pen. You will need a scientific calculator. And hopefully you've all brought your brains all switched on today for the activities we'll be doing today. We're going to do an introduction of what A-level physics is about, and then we'll look at some theory which you should have learned from GCSE and move that on to a bit of A-level physics. You will then see a demonstration on electron diffraction, and we'll finish up with an activity on working out the wavelength of electrons. I'm expecting it to be lots of fun. To start us off, I want you to think about why you want to study A-level physics. What is it that makes you want to study A-level physics? Pause the presentation and write down your top 3 reasons before, when you finish, then you can resume and carry on. This is what some past students have said. I wonder if they're similar to any of your top 3 reasons that you've written down. Robin said, I was good at maths and science at school, but I chose physics because it has applications in the real world. And there's also some status in doing physics as no one understands it. So when you study physics, people think you're super smart. I don't think that's true, but some people think. Alisa says, I was best at music at GCSE and I found science dull. I did physics and music at A level as I wanted to be a music producer. There are so many things that physics leads into, which are not pure physics, but your physics knowledge will help with. He said, then I began to enjoy physics more. It gets more interesting as you get into it. I found maths difficult, but now I see the point of it. It all has meaning. The more you study physics, the more interesting it gets. Physics is a really interesting subject with lots of things to fascinate you. Jenny says, I have a keen interest in it, but not a vast knowledge of it. I love reading the papers, the articles. I love the workings of the universe and man's understanding of it so far. I realized that people with physics degrees usually found themselves working interesting jobs, even if they weren't professional physicists. So there's so many interesting things, and I'll show you that in a few slides from now. Different things you could do with physics. So it's really, really versatile. John said, I chose it because it helps describe and explain the world I call home. For me, that would be my top reason, really. Physics is all around us all the time, and it's just fascinating to be able to explain the things we see with our knowledge of. Robert says, I've gone into a less fundamental branch of physics, which is medical physics, where most of the problems aren't so much about the fundamental laws of the universe, but how our understanding of these laws can help cure diseases and provide people with a better quality of life. Medical physics is a really interesting and useful branch of physics, which helps people use their physics knowledge in curing diseases, which is quite cool. Daniel said, I did it because someone bet me that I couldn't because I wasn't smart enough and I had to prove him wrong. To be honest, I'm not sure that's the best reason for doing A-level physics, but there we go. What careers can lead from A-level physics? There's so many things. As you can see in the picture below, there are the obvious engineering and science courses, but there are also things that you might not think about. Law, so many things that, physics can lead up into. And here is just a list of occupations that use physics knowledge. I'll just give you a few minutes to quickly have a look at the different things. Some you might be familiar with, some might be a surprise to you, thinking about the things that you could do with your physics knowledge. There's really no limit to where physics can take you. It's just so wide and so useful. Okay, so let's look at some theory. You should have learned about waves from your GCSEs. So thinking about what you know about waves, the properties of waves, can you mention and explain some properties of waves? I want you to just pause the presentation and write down a sentence or draw a diagram to explain the properties, whichever one suits you. And when you're done, just resume the presentation and see if you got them right. These are the properties that waves exhibit. There's reflection, refraction, diffraction, and interference. How many of the four did you get? I'm going to skip reflection and refraction because they are basic GCSE, even key stage 3 knowledge. And I'm just going to go on to diffraction and interference because that leads on to what we're going to be doing today, which is our A-level knowledge in physics. So diffraction. This picture shows diffraction is simply the spreading of waves when they pass through a gap or when they travel around an obstacle. So you can see the waves in the first picture passing through a gap and spreading out, and in the second picture you can see the waves going around an obstacle and also spreading out as they do that, and that is simply what diffraction is. Interference is when waves combine somehow, and there are two ways waves can combine. They can combine constructively, as we can see in the picture here, where wave 1 and wave 2 combine to give you a wave with a bigger amplitude. This is constructive interference. And we can also have destructive interference where the waves combine in such a way that they seem to cancel each other out, as we can see in this picture. These two things, two properties of waves, are used in this experiment called the Young double slit experiment, which is an experiment you will meet at A-level physics. In this experiment, you have a source of a wave here. It can be any wave. We can do this with light. We can also do it with sound. You have a source of a wave here. So if we're doing this with light, for example, we have a source passing through a gap here. So that's our first screen with a little gap. And we also have a second screen here with two gaps. The source will pass through the first gap, and because it's passing through, the wave is passing through a gap, the waves will diffract, and you can see the waves spreading out after the first screen. When they pass through the second screen, they would also diffract through the two slits, S1 and S2. You will then have two waves, one from S1 and one from S2. These two waves will travel towards the screen, which is further away, and you will find the two waves interfering. You will then see an interference pattern on the screen. This interference pattern will have different sections. In some places, the waves will interfere constructively, and in other places, the waves will interfere destructively, which you will see on the screen as spots where there's light and other spots where there's no light, which is your maximum and your minimum, as you can see on the screen. If we did this with green laser lights, this is what you would see. Your constructive interference is where there's green, and your destructive interference is where they're black. There's no light, which is, you can see as black spaces in the picture. So this experiment shows us two properties of waves, diffraction and interference, happening at the same time. Let's link that onto electrons. Question: are electrons waves or are they particles? What would you say? I want you to write down your answer with the reason. Would you say electrons are waves, or would you say your electrons are particles? When you finish that, just carry on with the presentation. And the next bit is where we're going to watch a video about electrons diffracting. Just pause the presentation and use the link below to watch the video, and when you finish, just resume the presentation. So we have just watched a video where we have seen electrons diffracting. Straight away, if you wrote down the electrons were particles, you'd be thinking, well, how can a particle diffract? But we know traditionally the electrons are particles. So what's going on here? There's something called was first of all found by the American physicist Arthur Compton. He did some work on X-rays where he discovered that X-rays collided with electrons behaving like particles. This started the theory that electromagnetic waves could be considered as a stream of particles called photons. So even though electromagnetic waves are traditionally regarded as waves, they could actually be considered as a stream of particles. In 1942, another scientist extended his theory. Louis de Broglie extended this theory, suggesting that electrons, protons, and neutrons possess both particle and wave properties. This is the origin of the wave-particle duality, which is now the basis of quantum mechanics, which is a big branch of physics now. So we can see electrons, which traditionally are regarded as particles, behaving like waves sometimes because they can. And this is the experiment we just looked at. This is showing us electrons behaving like waves. Electrons are diffracting and interfering. So electrons behaving like waves because they exhibit this wave-particle duality, sometimes behaving like waves and sometimes behaving like particles. So whichever answer you wrote, electrons are waves, electrons are particles, one way or the other, you're right. So if electrons can behave like waves, it then follows that they would have a wavelength. But the wavelength would not be the traditional wavelength you're used to when you study waves, or v is equal to lambda times speed. You're looking at a different kind of wavelength. This wavelength is called de Broglie's wavelength, and the wavelength of the electrons is given by the equation. Wavelength is equal to h, which is a constant called Planck constant, divided by the momentum of the electron. We're going to use this in activity today. We're going to be doing some maths. So electrons accelerated through a potential difference before striking a layer of graphite, as seen in the electron diffraction experiment you just looked at. In my experiment, I've used an accelerating potential difference of 4,000 volts. In the video, it was 3,000 volts or 6,000 at the end, but I have used 4,000 volts in my experiment, so I've put 4,000 volts as my accelerating potential difference. And this is some other data that you would need for the experiment, for the calculation you'll be doing. When you see, I showed you the diffraction pattern, there was a central dot in the middle of the diffraction tube, and then there were rings around the tube. Those rings are called the orders of diffraction of the tube. So the first ring is the first order diffraction ring, the second ring is the second order diffraction ring, and so on. So theta is the first order diffraction ring angle, which I've given you as 6.2 degrees. And the rest of it, the mass of the electron, the charge of the electron, Planck constant, velocity of the electron, de Broglie's wavelength, and all the other things. Okay, so that's some data you would need. You'll probably need to come back to this slide when you're doing your calculation just to pick the data you would need. This is some useful equations you would need as well. The potential energy of the electron you can find by calculating the charge of the electron times the accelerating potential difference, the kinetic energy, the de Broglie wavelength, and to extend you, that's a purely A-level equation. The order of diffraction times lambda is equal to d sine theta, and all those things have been given you in the data. Your first task is to calculate the energy of each electron when it reaches the graphite and the speed of the electrons when they hit the graphite. Pause the presentation now and do these calculations on your notebook, and when you finish, resume the presentation and check your answer. What equations and data did you pick out to help you do the calculation? So the ones you would need are the energy of the electron, which is EV, and the data, The accelerating potential difference is 4,000 volts and the charge is 1.6 times 10 to the power minus 19 coulombs. So to work out the energy, you just calculate EV, which is shown in my calculation, 1.6 times 10 to the power minus 19 times 4,000. The energy of each electron when it reaches the graphite would be 6.4 times 10 to the power minus 16 joules. Did you get that right? Give yourself a tick if you did and a pat on the back. Second part of that question, to calculate the speed of the electrons when they hit the graphite, you would need the energy of the electron, which you should have calculated in the previous question. You would need the equation for kinetic energy, half mv squared. You would need the mass of the electron, and the velocity of the electrons is what you're going to be calculating. So if you use all of that, you would use the kinetic energy would be equal to the energy of the electrons, which you calculated previously. So half mv squared is equal to 6.4 times 10 to the power minus 16 joules. You can rearrange that equation to make v the subject, and that will give you the velocity of the electrons to be 3.7 times 10 to the power 7 meters per second. Did you get that right? Second part of the question is to calculate the wavelength of the electrons. Pause the presentation now and answer the next question, showing your full working out. Remember, pick out the data that you need from the slide containing the data and what equation you would need. When you're finished, resume the presentation and check your answer. So you had calculated the velocity of the electrons as 3.7 times 10 to the power 7 meters per second. And we know from the equations I gave you that lambda, which is the wavelength, is Planck constant divided by the momentum. But momentum is mass times velocity, which you should know from GCSEs. So plugging that into the equation, the wavelength is equal to Planck constant divided by mass times velocity. Plug in the numbers you have, and you should get for the wavelength 1.97 times 10 to the power minus 11 meters. Did you get that right? Give yourself a pat on the back if you did. And the last bit, calculate the spacing of the graphite particles. So I've talked about the order of the rings. The first ring is the first order, the second ring is the second order, and on and on. So pause the presentation now and answer the question to calculate the spacing of the graphite particles. When you've finished doing your working out, resume the presentation and check your answer. Using the equation, n times lambda is equal to d sine theta. N would be 1 because I gave you the first order diffraction ring angle. So put all the values in the equation and make d the subject. You would get d to be equal to 1.8 times 10 to the power minus 10 meters. How did you do with that one? Give yourself a pat on the back if you got it right. How did you get on with the activity? Answering all the questions. I would like you to pause the presentation now and write down one thing you found easy, one thing you found hard, and one thing you found interesting about carrying out that activity. When you finish, resume the presentation. Do I have to study A-level maths if I choose A-level physics? That's a question a lot of people ask me. And it's a valid question. So I have given you an activity to do that has to do with just maths, really. There wasn't much physics in what I've asked you to do today. Because maths and physics go together, there's so much maths in A-level physics. My answer is that, first of all, you need a minimum of a grade 6 at maths GCSE to get onto the course. And we found from past experience that students who do not study maths, on average, are a grade or more below those who studied maths at A level. So your final physics grade at A level depends a lot on your maths knowledge. So I highly, highly, highly recommend that if you want to study physics, you should choose maths as one of your options as well. I think you will struggle if you don't. So while it's not compulsory, it is highly, highly recommended. The course structure, just to give you an idea of how the course runs, you own your own learning. Teaching is done by this method called flip learning, where you learn the stuff before you come to class. And when you come to class, all we're doing is you demonstrating to me that you have learned your stuff and me checking that you have understood what you should understand. So it's not me teaching you like you're probably used to at GCSE, waiting for the teacher to give you everything. That is not the way the course runs. You really, really need to take responsibility for your own learning and be ready to do everything you need to do before you come into the lessons. You'll be given weekly homework, which is a booklet of exam questions. It is so important to practice exam questions if you want to do well at A-level physics. So we'll do lots and lots of that, both in classroom and for your homework as well. At the end of every chapter, we do an end of chapter test. So we can keep on top of, you know how you're doing and I know how you're doing as well. So you can plug any gaps in your knowledge before it gets too late. Your progress is monitored through your weekly homework task and your end of chapter test. I keep a record of everything we've done and I kind of just rag rates to help me see where you are. So you're not falling behind, hopefully, before we get to know that something is wrong. And just a quick overview of the course. You study 6 modules, which are listed on the screen. Those are the 6 modules you're going to learn over the 2 years. The first 4 you will learn in the first year and the last 2 in the second year. Hello, welcome to A-level physics sister lesson. My name is Mrs. Daniels. I'll be one of your physics teachers. Hello, welcome to A-level physics sister lesson. My name is Mrs. Daniels. I'll be one of your physics teachers. Hello, welcome to A-level physics sister lesson. My name is Mrs. Daniels. I'll be one of your physics teachers.